section 9.1 now with one of the questions from the homework, at least my version of that question?
Yes.
Right, so let's just, sometimes it's just how they phrase it. So I'm going to go through this group of questions. I've got a kind of selection from 9.1 and then some more from 9.2. So a study of all the students at a small college showed that the mean age was 20.2 and that the standard deviation was 2.9. And they go in and they start off by just asking you, are these two numbers, are they statistics or are they parameters? And the way you answer that question is, if the numbers come from the population, then it is a parameter. If the numbers they're talking about came from a sample of 20 people or 200 people, it doesn't matter what the size is, then these things are called statistics. Now the key here is such a small word that you miss it. All. A study of all the students at a small college. That means this is a population that they got these numbers from, right? Because it was everybody. It wasn't we did a sample of 200 students from a small college, right? So if you see that, you know, read the question and hopefully there's a, you know, there's a clue to whether the information came from every single person and you got the average and standard deviation, or whether it came from a small group, subgroup of that, which would be a sample. So it goes on and says, as we say what these are, so the choices are, the numbers are parameters because they're estimates and not certain, and the numbers are parameters because they are from all the students, not a sample. So the choice here would be D. You've taken everybody, so you know it's going to be 20.2. Now there are 4 symbols down here that we typically use, and this textbook it certainly does, and you're going to be putting mu 20.2. Mu is the symbol, a Greek letter mu, mu, that's used to be the population mean. Which one of these ones, the S or that funny little Greek letter sigma, is the letter that you use for the population standard deviation? Anyone? Population standard deviation. What letter do they use from this list for that thing? Mu is for the mean, and, okay. See that funny little fella there that looks like a zero with a hat on it? It's called sigma. That's the standard deviation symbol. Okay, let's look at another question, this one here. Make this a bit bigger. That might help you see it. Right, I'm going to read this question. We're going to go in and we're going to go out, and well, we won't go in and out in this one, but let's see the difference between the first one. A survey of 100 random full-time students. Already know the answer, don't need to read anymore. That's a sample, right? So these numbers that we're about to hear about, these are going to be the numbers that you got from a sample, which means that these numbers are going to be statistics. So we go through the list and we pick statistics, and the number of statistics, because they are sampled from, they're a sample of students, not all the students, so you would pick D. And X bar would be used for the mean of 17.5, and S would be the standard deviation. So that's very quick warm-up questions. In this story here, they're getting, to remind you of the bell-shaped curves, and the particular one that we're doing is a 75 one. The mean is 70 and the standard deviation is 5. Now, if you look at this picture, the one that actually shows you that is A. Right, the middle is 70. And you see it goes up in 1, 2, 3 standard deviations, 5, 10, 15. Right, next one. Oh, any questions so far? Are we good? Nice, easy start, I hope. Right. Okay, let's see what's going on here. According number 5, I believe. According to the online source, the average shower in a country lasts 8.6 minutes. Assume that this is correct, and assume that the standard deviation is 2 minutes. Complete parts A through C. Here we go. It says, do you expect the shape of the distribution of showers to be normal, right skewed, or left skewed? Now, this isn't statistics. This is me just from what I know of showers. And so the answers are actually here. The distribution is going to be right skewed. So can you imagine 8.6 is the average. Some showers like don't happen more than a minute, but some showers, like, I wouldn't call them showers anymore, right? They could last for an hour. And so there's more to the right than the rest to the left. So that's why I chose right skewed, because the values are mostly small, but there are a few very large ones, right? They drift to the right. So when you look at right skewedness, look at where the numbers drift to. Then it goes on and says, suppose we take a survey of a random sample of 100 people and find the length of their last shower. Oh, okay. We calculate the mean length for the sample and record the value and repeat it 500 times. Right. So I'm going to leave this now and we'll start a little bit of theory. I just realized the shower that we're talking about is not rain showers. The shower they're talking about is taking a shower. Right. I'm going to look at what's called the central limit theorem. Now, you've done this same theory when you were looking at population proportions. Essentially what it says, if you take a large sample N from a population with a mean equal to mu and someone just joined us, and the standard deviation of sigma then the sampling distribution of the means will be normal in shape and have a mean equal to mu and a standard deviation, which is called the standard error. Now, when this was population proportions, the mean would be P, population proportion P, and the standard error, called the standard deviation, standard error, would be the square root of P, 1 minus P over N. Remember that weird formula? You used that enough? Square root of P, 1 minus P over N. New guy in town. It's sigma over the square root of N. So how can this work? Well, first we have to take central limit theorem. When can you use it? The sample needs to be random and independent. Secondly, sample has to be big. Thirdly, okay, now you can't see the question that we had a few minutes ago, but I'm going to now go through that question, right? So in this particular one, the mean length of a shower was 8.6 minutes, and the population standard deviation for this was 2 minutes. Fair enough. Suppose we take a sample of 100 people, and then we conduct that 500 times. That's the shape that you would get. Right? Imagine 500 times you did this. 100 people, 500 times. 100 people, 500 times. Let's go through the list. Random and independent. It was a random sample, so that's good of 100 people, and we'll assume, because there's no reason to assume not, that it's independent. Yes. This is a little bit vague. When it was populations, proportions, then we just do n p hat, n 1 minus p hat, and as long as they were bigger than 10, we went and said that the sample was big enough. You remember that rule? Well, when you do it for means, let's say it has to be bigger than 25. It's a kind of arbitrary number, but most people would accept that you at least need 25 people in your sample to have a fighting chance of using this. And then population has to be big. And we would certainly say that in the context of this question, that's typically guaranteed. Now for this particular sample size 100, its mean is going to be mu, it's 8.6. And the standard error, standard deviation if you prefer, is going to be sigma over the square root of n, which is going to be 2 over the square root of 100. It's going to be that. So that's the new way that we're going to approach calculating what the sampling distribution looks like. It's going to be normal in shape. It's going to have the mean the same as the population mean, and it's going to have a standard deviation called standard error of whatever the population standard deviation is divided by the square root of n. And that kind of is the gist of most of what's about to happen. So let me return. Is there any questions yet? Are we back to seeing the screen where the questions, homework questions are? A yes or a thumbs up would be good. I can't see what you can see.
Yes.
Right, we're good then. Right, okay, so in that particular story here, the mean would fit in here, right, and the standard deviation here. So the mean will be, well, I can't do that now, but if you clicked on that, you put mu and then you put your number. So here's another one. The average income in a state is 50,000 per person per year. Suppose that the standard deviation is 25,000 and the distribution is right skewed. The cool thing about the central limit theorem is it doesn't care if the population, the numbers that make up that population are skewed left, skewed right, or any other in-between shape. as long as your sample is big enough and your population is big enough, you can use the fact that the sampling distribution will always be normal in shape. So in this particular case, the random sample of 100 is the complete right. So what value would you expect for the sample mean? I'd expect to get around about 50,000, because that's typically what you would normally get from a sample. You get an answer that's very close to whatever the mean is. And that's about all we can do. Oh, and the standard error, which you can't see here, wouldn't it be 25,000 divided by the square of 100, which is what? 25,000 divided by 10, 2,500. And that's the end of 9.1. So what we're going to be doing in 9.2 is just continuing from where we left off. We're going to be looking at the sampling distribution, and we're going to use it to calculate various probabilities. So this first one. Some sources report that the weight of a full-term newborn baby in a certain town has a mean of 9 pounds. Oh, that's quite heavy. And a standard deviation of 0.6. Now, since those two numbers are from the population, you've just told me that mu is 9 and sigma is 0.6. And now it's asking us, what's the probability that one baby from this population will have a weight within 0.6 of the mean? So I'm going to now kind of read those questions to you because I want you to see what I'm writing. Okay, so mean in this population, 9 pound babies, standard deviation 0.6. It says, what's the probability of one newborn baby will have a weight within 0.6 of the mean? And then they give you some numbers and they describe it in terms of standard deviation. So if I draw a little picture of what that would look like, this is the population. We haven't done any sample yet. Right in the middle is 9. And one standard deviation either side takes me to 9.6 and 8.4. And we're being asked to find what's the probability of that happening. You're going to have to think back. But can you remember roughly what percentage, and that's going to be the probability, do you get within one standard deviation of the mean of a normal distribution? Between one either side of the mean. The answer is 68%. And here goes for the second one then. What happens if you go plus or minus 2 standard deviations? What percentage does that get you then? So the first one was 68. The second one was?
95.
Yes. And it depends on what textbook you use. But if you go 3 standard deviation, it's either 99.7% or they use the words almost all. You remember that guy? Right. 68, 95, almost all. So in this question here, 68%. What's the probability that the average of 9 babies will do that? Now we are taking a sample of 9 babies. And in this case, the mean is still going to be 9, but the standard deviation is going to be sigma over the square root of 9, which is going to be sigma divided by the square root of 9 0.2. Now if you put 9 in here and you do 0.6, isn't that 3 standard deviations away from the mean? So the chances that you get an average, right, within that's within 0.6 of the mean, right, is 3 standard deviations away. So the answer to that will be 99.7%, or almost all. So one baby can be within 1 standard deviation of the mean 68% of the time. But taking an average of 9, that's pretty much almost guaranteed. Because you're going to get a little baby who's 10 pound and another little baby that's 8. But when you take a sample of 9, the chances are that they kind of average out, and that makes the mean tighter. In other words, there's less variation because of that. And that's what they're going about when they talk about Part C. Any questions so far? Shall I move on then? So the average income in a certain region is 67,000 and the standard deviation is 27,000. So they've just told me the population mean is 67,000 and the standard deviation is 27. Suppose we take a random sample of 100 residents. Right. Is the sample size large enough? Well, the rule for that is that you need to be at least 25, so 100 works. We're good. What are the mean and standard deviations of this sampling distribution? Well, if you took this 100 people and you did it lots and lots of times, you'd get this thing called the sampling distribution. Its mean is the same as the population, so it'll still be 67,000. Its standard deviation won't be this guy. It'll be this guy divided by the square root of n, which in this case is what, 10. So you'll end up with 2,700. And then it says, what is the probability that the sample mean will be more than 2,700 away from the population mean? Can you imagine what they're just saying is 1 standard deviation either side of the mean? And that we have got already as 68%. Just checking our time, right? The next question, the mean age of 692 used cars for sale in a newspaper one Saturday last month was 7.8 years and a standard deviation is 7.6 years. Okay, so our population is 692 here. The distribution of ages is right skewed. For a study to determine the reliability of classified ads, a reporter randomly selected 50 of these cars and he visited the owners and he finds that the mean age of the 50 cards was actually 8.2 and that the standard deviation of these 50 cards was 6.1. And then we go through a whole set of things. In this particular case, all we're doing is labeling what these numbers are. So 7.8 is the population mean. 7.6 is the population standard deviation. 8.2 is the sample mean. And 6.1 is the sample standard deviation. And that's the end of that question. So here's a similar one. The mean age of all 2,500 students at a small college is 22.5, and the standard deviation is 3.8, and that is right skewed. A random sample of 5 students are obtained, and the mean was 23 and the standard deviation was 3.3. So here we go. They're asking us to fill in what sigma is, and that's 3.8. What X bar is, sample 23. What S is, 3.3. And it asks us now, is mu a parameter or statistic? Mu is a parameter because it comes from the population. And it says in C, are the conditions for the central limit theorem fulfilled? And the answer is no. The large sample condition is not. The large sample condition says that shouldn't your sample be at least 25? And can you see over here? It's only 5. So it says, what would you expect the shape of the sampling distribution to be then when you only use 5 students? I expect it to be the same shape as the population shape. And according to them, this population is right skewed. So when the sample is small like this, I'd also expect it to be right skewed. Is that all pretty straightforward about what things are labelled, what their names are, and a little quick example of why the central limit theorem can't always be used, in this case, because the sample was too small. About to move on. We good? Okay. Oh. And what I'm going to do now for the last question is going to give you a kind of start to finish question of what this would look like in a typical situation. So I'm going to make up a story, and we're going to have a number of parts to it. So this is the story first. So we have a large population of elephants. I'll abbreviate it. The mean age of these elephants is 50 years, and the standard deviation is 10. In this story, we take a sample of 100. And we get a mean of 60. Let's make even less obvious. We get a mean of 55. Is this an unusual event? So that's part A. And part B, we take a sample of another 100. And we want to know this time, what is the probability that the mean of this sample will be greater than 5.3. Okay, so we've got 2 questions based around a population of elephants. So I should go through central limit theorem test. Sample is random, yes. Is the sample size 100 big enough? Yes. Is the population big? Yes, they told me it was large. So we're allowed to use the central limit theorem. Let's use it for A. The sample mean here is 55. And the standard error is sigma over root n, which in this case is 10 over the square root of 100, which I made my life really easy, and it ends up being 1. This mean was 55, and we are trying to see, is that unusual? Well, we should get a population mean 50, and the standard error is 1. Do you see the guy that we've got here is extreme? It's in fact 5 standard deviations away from the mean. In statistics, if you take a number and you find out how far away from the mean it is, most numbers typically are very close. They're maybe within 1 standard deviation of the mean. That's where 68% of the numbers are. If you went 2 standard deviations away from the mean, that's where 95% of the numbers are. If you go 3 standard deviations away from the mean, 99.7% of the data is there. See the guy we've got, he's even further out than that. So that's why the answer to this question would be yes, it is a very unusual event. Part B now. What's the chance that you get a mean that's greater than 50.3? The normal distribution for this particular thing is mu, and the standard deviation is that guy, which we already have calculated is that fella. So you're being asked to find what's the probability that you can get a greater than 50.3 from this fella. You're actually going to go back to a guy you haven't used for a while. You're going to use the normal CDF. And you want greater than 50.3, so you go 50.3 or bigger, with a mean of 50 and a standard deviation of 1. So mu is going to go there, standard error is going to go there, and that guy is going to go there. Do you think that number is going to be quite big or quite small? What's your gut feeling? Has anybody got a gut feeling? I mean, the population's 50 and your sample is 50.3 or bigger. While you're thinking about that, I'm actually typing it in to find out. And the answer is 0.38, roughly. Yeah, it could happen. About 38% of the time, actually, it's going to happen. If I try to do the same calculation with this thing up here, the calculator would almost certainly have said the answer is 0. So if I went and put in 55 instead of that number and kept the rest the same, this number here would end up being either 0 or so darn close to 0, no one else, you wouldn't be able to tell the difference. And that's a pretty typical kind of question from that section. Well, I'm about to finish off at this point. Is there any general questions you want to ask? Okay, Bill, before you go, let me tell you, you already should know when your final is. Does anybody want to mention the day?
Isn't it next Friday, 1 to 4?
Yep. It's totally comprehensive, so that's from chapter 1 to chapter 9. When I have time, sometime probably tomorrow, when I get to round to it, because I'm kind of busy right now, making up the finals, I'll be putting up a formula sheet so you can see in one place the kind of formulas that you'll need to know and use. And I'll be putting up a kind of, I guess it's like a practice final, just something so you can get an idea of the kinds of questions that you might expect. It's going to be from your math, your software that you use, MATLAB. What else? I know I've got something else to tell you. What else was it? It's escaped me. Obviously, it wasn't that important, or it would have came to me. So you know when your test, you know when your final is. Oh yeah, I remember now. On Tuesday, you will get the chance, those who want to take part in a replacement test, and that will be that will appear early on Tuesday and will have to be completed by midnight. And the test that you've just done. Still working on grading those. It takes a long time since I have 5 classes, but I'll try and get them up and running sometime by the end of tomorrow so you can get an idea of where you stand right now. I think that's everything I need to say. So I'll thank you for turning up. If you need to see me about anything, as always, shoot me an email. You can make something happen. Bye-bye.
Thank you.